when you study nuclear reactions, one of the items in nuclear reactions is nuclear fission. Now, nuclear fission occurs when you're having an external kind of stimulus in order to kickstart the actual reaction. So it isn't like the nuclear reactions of alpha decay, beta decay, gamma decay, which basically are caused by kind of an instability on the internal nucleus of that isotope that we have, so the radioisotopes, and they start kind of jiggling around and then breaking things up, and then you have alpha decay, beta decay, or gamma decay, or electron captures occurring. Well, in nuclear fission, it's not necessarily completely unstable. There's some external starting point to kickstart this process. So that is the nuclear fission. And what happens in nuclear fission is that, so you have the reactants, and then you will have products. Now, your products, so the daughter products, are going to be different than your actual reactant starting point. But as you can see here, so in the general equation for nuclear fission, the reactants that we have in here that we can place in right here, here are some examples. So uranium, both 235 and 233, thorium and plutonium. So those are some examples that can kind of kickstart this process within here because they're fissionable isotopes where they can take in and be broken down into products. With that, once we kickstart this and we kind of almost like launch into this particular atom, okay, so this isotope, and we can dislodge the actual nucleus into various products. So these are called the fission products that we would have. Now this will depend, it's not always consistently the same that you would have these happening, but there are, and I'll show you an example of one in particular so that you can see. But you can understand the reactants and then the products just even going back to chemical reactions. So that's one of the things that can certainly happen. You have seen products as well when you're talking about nuclear reactions in general. So from alpha and beta decays, for instance. Now, one of the additional items that happens in these fission products is that there is also some neutrons that get dislodged. And this will depend on how many neutrons you have and how many get kicked out. Now, the ultimate thing with regards to fission and the nuclear reaction, so the nuclear energy that comes about through this process, is this extra energy component. And it is actually relatively huge in comparison to many other reactions. So when this happens and it kickstarts, now if it's only one, it's already relatively big with respect to that one. But if this happens and continues on and has a chain reaction, then it becomes quite dramatic. So we can extract quite a lot of energy in nuclear energy to fuel our homes or anything else on the grid. But of course, it can be also destructive in nuclear weapons. So now, these kind of starting isotopes that we have, so the uranium, the thorium, the plutonium, so these are called fissionable isotopes because not all of the actual isotopes are fissionable where you can break them up into separate components. So there's only a few. So here are kind of the most common ones that you have in here. Now, I mentioned that it produces a huge amounts of energy. Well, so this is in quotation marks because I've taken this information from a textbook and I'll put it in the references in the description as well, and I'll show it momentarily. So the amount of energy produced during this nuclear fission, so during this process right here, is about 7 million times as great as the energy released during a dynamite explosion in comparable size. If you had the same amount of mass and the same amount of mass, then it would have been, if the same amount of masses, the nuclear fission process produces 7 million times more. Hence, these nuclear energies and destructions that can happen. That's pretty enormous. Now, when we take this in, and I'll just talk about the nuclear energy component, so in nuclear reactors, for instance, when we take this and we call this kind of the nuclear fuel that we would have. So these are these nuclear fuel in here. So as I'm writing it out in here, so this, I'm going to draw your attention. These are the fissionable isotopes in this nuclear fuel. So you can think of fuel even in terms of gasoline. If you're powering up your car, you know, you can talk about kind of natural gas, okay, to heat up your homes or anything of that nature. So you're familiar with fuels in general. Well, we have these particular fuels, and they're actually filled with these fissionable isotopes, which allow us for this process to take place. And these fissionable isotopes, okay, if you have enough present of them, then they will, so now when we say enough, it means it creates this critical mass. So you need a certain amount of it in order to kickstart this chain reaction. So initially we throw in this neutron within here. It breaks down these products, but because of the fact that we have neutrons coming out, and sometimes you'll have 3 neutrons, and these neutrons can now kickstart other reactions. So you'll start with one, it's almost like a domino effect, where you kick up one and then it just domino affects other reactions, and it will start burning out the fuel. Now, of course, in this case, it's the nuclear fuel that we would have, and it would produce a huge amounts of energy where we want to capture it and then use it for something else. Now, in this process of this nuclear fission, these neutrons, typically, when they do get released, they carry just way too much energy to actually kickstart other reactions. And in order to bring down their energy a bit so that they can continue on and start kicking back the processes, and this is in the nuclear reactors when we create this energy, then we have this neutron moderation process. So we want to moderate the amount of energy that it has, and typically we utilize pretty heavy water with deuterium, which is, if you recall, is just hydrogen, except now it's the isotope 2, so it has a proton and a neutron. So it's much heavier than regular water. So we will utilize this and it will moderate, okay? And this is needed, okay? And its released neutrons carry too much energy. So the need of this moderation is that in this process, in the nuclear reactors, this will carry too much energy. So because it carries too much energy in here, that's what we have, we're creating this process to just kind of subdue it and moderate that so that it can continue on and create other reactions. So that's the process. So we have these fissionable isotopes. We can kickstart this process. They break down, and now you're going to have different isotopes carried out. These are the fission products released. And then you'll have some neutrons that can possibly kickstart other reactions as well. And you have this energy. Now, this energy is what we want to try to capture and use it for useful items. So if you wanted to visualize this process, so here's an example, and I am literally stealing this from the physics textbook. Okay, this is a grade 11 textbook by Nelson. You have the authors there, and again, I'll put it like pretty much all of the physics videos I've done. I've always referenced this because that's where I pretty much get the material, you know, aside from some other places. For example, nowadays, you know, like ChatGPT, which can guide you quite a bit. So as you can see here, what you have is, this is the reaction itself. So this is uranium. Now this is uranium-235 right there, as you can see there. Here's the neutron, which kind of gets shut out at this. And what happens is, okay, this gets broken down, and it gets broken down into, so in this case it's barium, okay, and then here, okay, so we have Kr, okay, so that's what we would have in there. Now, within these two processes that we have, notice that there's neutrons which are also released. And of course, there is energy as well. So that is capturing this entire process that we see right here. Let's see this in action, and let's do a calculation to see how much energy actually comes out just from one single reaction. Of course, the more mass you have, the more chain reaction you have. This gets bigger and bigger and bigger. So here's the example written out as a nuclear reaction itself. So this is nuclear fission reaction. So notice here's our U, so here's our KR, our BA. So these are the items, so these are the products that are released in here. So these are the fission products. Here are the neutrons, okay, that are released. Here's the energy. This is what we're going to be trying to calculate from this process. And then here is your fissionable, in this case, so this is your starting reactants that you have, and the thrown in neutron, which starts and kicks off the whole process. So let us assume that we have these atomic masses. So these are all the atomic masses that we have. Notice that, there's only one of each of these. Now we have one neutron on the left, 3 neutrons on the right. So here is the actual atomic mass unit that I provide. Now I give you a recall, so atomic mass units in terms of comparison to kilograms, because we will need that if we want to calculate the energy. So our goal is, how much energy would we have over here? And we can change that energy to mega electron volts as well. All right, so we'll keep it in joules and in mega electric volts as a practice run. So let's try this. How would we go about this process in terms of calculations? Well, so we want to be able to calculate the mass, the mass defect, okay, in between. Now, if you recall the mass defect, I'll put up a link up above there. We were talking about the mass defect with regards to binding energies for a particular isotope, right? So we were trying to see what the difference is, and that binding energy, it was a comparison between the fact that energy has an equivalence to mass, but we were talking about just one item, and you can see that in the link that I provided. In this case, we're not talking about one item, we're talking about the reaction in general. So our mass defect is going to be between the reactants and the products. So we want to see what is the mass defect, okay? The mass difference in between. So this has a certain amount of mass, right? So we have, here's uranium, okay? And then here's going to be the neutron over here. And then, here are your products. So here are the ones that we have. So that is 1 and 2. And then you have the 3 neutrons in here. And then this right here is going to be almost like the binding energy, but it's not the binding energy because it's not binding anything. It is actually the energy that gets released out. Okay, so that's what we want to be able to calculate. So how do we do that? How do we go through that process? So we will take in the products. So we want to know what was the mass of the products minus the mass of the reactants that we have. So let's do that. So within here, so the products, I'm going to do it in atomic mass units for here. So I have them listed right here. So this is KR, this is BA. So these are provided to us. All right, so let's take a look here. We have in here, so if I take a look, so this is going to be 91.9261,560 plus this is going to be 140.9144033. Okay, now out of these I still will need, so if I go back to this, notice that I have 3 neutrons in here and I'll have 1 neutron over there. So technically, if I'm subtracting them, I guess it's 2 neutrons altogether. Now, how you do this is up to you. I'm going to actually just write it in and say plus 3 times the mass of the neutron in here, which is 1.008664915. That's right from the table. Now, those are the masses of the products that have been released. Now, what about the reactants? So I'll do this in blue. Well, the reactants I only have, so within here, so maybe I'll steal this so that it's a little bit faster. I'm going to copy this, bring it back down. So this is what I have. That is my uranium plus the additional, now here I have it right above, plus the neutron, which gets shut out at this. So this is going to be that. And that would have been my total mass So my mass defect, so the mass difference really, right? So this is the mass difference that I have in here. So from what I started to what I ended up with, I'm going to have a difference between these. Now, this mass difference, as you're going through, is going to be what you want to be able to calculate and see. Now, for us, because the energy is released, so in here, what I've done is I've actually kind of reversed these in, so we would have gotten a negative number, okay? So because I took the products first, okay, minus the reactants. So we will, so I'm going to start actually, I'm going to do the reverse. I'm going to say the reactants, okay, so within minus the actual products. So let me just reverse this instead of writing it out like this. I'm going to take this out. I'm going to move it over, okay, so within here. So this is what I'll have, because I want to be able to see, okay, on the product side how much energy has been released. So let's try this. I'm just going to kind of reverse these back in and take out my calculator. So I'm going to take out my calculator. I'll do the calculations. I'll be right back. So there you have it. Okay, so that's the difference. Now, if you have done products minus reactants, it would have been negative, and that would make sense because now it's the actual release of the energy that you would have. So this is just the mass. Now, in terms of trying to change the mass, and if you want the mass in kilograms, because ultimately what we want is we want the binding energy. Okay, now, again, it's not binding anymore. We want the energy released. And that comes back into our kind of famous Einstein's equation, energy is equal to mass times c squared. And I can't substitute this for mass because I need it in kilograms to make it in metric SI units. And then the speed itself, now you can use the speed which is rounded, whatever it is that you like. I'm going to use the speed as just 3.0 times 10 to the 8, so this is definitely rounded, and I'll round my answer to 2 sig figs as well. So let's try this, okay? So the mass itself, so I have the mass right there, so this is my answer, times, and that's going to be the mass of 1.66, okay, 05. Now, I have put in a huge amount of decimal places. Of course, you don't have to carry them. You can check with your teachers how many they want you to have within here. I'm just keeping it in here just for the sake of completeness. Okay, so this would have been now my mass of that. I'm not going to write that down. I'll just keep it on my calculator. Now, once I have this, I have to now take this and multiply it by the actual speed of light squared. So I'm going to take this now and say, so 3 times, this is going to be 10 to the 8. That's the speed of light. Now I'm going to have to square that and then hit equals. And this is what I have. This is the energy just for one reaction, just one. So this is around 2.78. So since I've only used 2 sig figs, I'll use 2 sig figs here. Times 10 to the negative 11. This is joules. And if you want this, right, so coming back in here, if you want it in mega electron volts, which is a much more convenient way, especially when you're doing this on such a small scale, then you can certainly do that and take your answer. And so take your answer and then divide it by that. So which is 1.6021766, This is going to be times 10 to the, and this is negative 13. So I'll put that in here. And that now gives you how much energy. So so in this case it would have been 173.5. Again, if you want this to 2 significant figures, it's about 170 mega electron volts. That's just per one reaction. So if you have obviously quite a lot of this nuclear fuel around, so these particular fissionable isotopes, in the fuel, then this reaction is going to be enormously generating huge amounts. And here is an example of how you would calculate what that energy will be. All right, so I hope that this helps you in understanding these nuclear fission reactions and gives you some little bit of intuition so that you can now tie in everything from just regular chemical reactions. Then you can kind of go into nuclear reactions, which are from the alpha decay components, beta decay, electron captures. That's what you can have there, or gamma decay. Okay, and then finally these nuclear fission reactions. So if you can capture all of these and understand what is happening on both on the nucleus side and then on the chemical reaction side, which is more on the bonds between them, then you have a good grasp and understanding of these concepts. All right, so thanks for watching, and we'll see you in future videos. Bye, everybody.